Hello Math 1224, this is Dr. P with Lesson Launch 503 in my humble estimation, because this video is all about different ways of estimating integrals. So for this video, I've produced a graph of a function f whose formula I'm not going to give because having it frankly wouldn't help. I created a formula for a function that I know couldn't be integrated analytically and used GeoGebra, which you might find to be a useful tool, so I'll write that down. Use GeoGebra, which is a free download, to produce the graph. And now I want to talk about how we might estimate the integral of f, the integral from 0 to 5 of f of x dx. We're going to estimate that, and do that in several ways, a couple of which you will have seen before, and a couple of which might be new to you. Alright, so the first way we're going to estimate the integral from 0 to 5 of f of x is to draw a Riemann sum. You remember, a Riemann sum is gotten by dividing this interval from 0 to 5 into some number of subintervals, and I'm going to pick 5 just because it works nicely with the grid lines here, but I could pick any number I want. So I'll pick 5 subintervals. And the way I'm going to estimate the integral is for each interval. God, those two words sound an awful lot alike, integral and interval. But for each interval, I'm going to pick a value of f of x that I'm going to use as the representative value of f of x for that entire interval. And I'm going to use the value at the left endpoint in each case. So the value at the left endpoint for this first interval is 4. And then the value for this interval is about 1.5. It's not exactly that. And then for this next interval, it's a little bit less than 1. And then the next interval about 1/2. And the last interval is going to be somewhere between 0 and 1/2. And then to estimate the integral from 0 to 5 of f of x dx, I'm going to add up the sum from I equals 1 to 5 of f of something. And this time I'm going to try and state what that something is exactly in terms of I. Well, when I is 1, my first summand is going to involve f of 0. My second summand is going to involve f of 1. So I think what I'm adding up is f of I minus 1 times delta x. And that delta x, this is kind of inconvenient for this example, but that delta x is 1. So it's going to look like that delta x is going away, even though it's still there. I'll just write a 1 there so that we remember that there is an actual factor under consideration there. There, that's my delta x. Okay? And a way that we can represent that visually is we can think, okay, what does it look like if I take a function value, which is the length of some vertical line in this picture, and multiply by delta x, that's the width of an interval. Well, if I multiply those two things, I get the area of a box. The area of a rectangular box. And I'm going to get one of those for every summand in that sum. So I'm going to get 5 rectangles. And then the sum of the areas of those 5 rectangles, just shade those in there, the sum of those areas, that's going to be an approximation, an estimate, for the integral from 0 to 5. Now, one question we might want to ask ourselves is whether this estimate is going to be too high or too low for the actual integral itself. And in this case, we can see that the estimate is going to be higher than the integral because we are taking into account a greater amount of area than what is actually under this curve. Anyway, this estimation method is called the left-hand sum, and in this course we're going to represent that as left, and then parentheses, the number of subintervals that we used. So we used 5 subintervals. So we're going to call that left of 5. Just as a reminder, I'm going to write down that means the number of subintervals. Alright, so that is a left-hand sum. Now you've probably heard of this one before, and you know by now that this is a useful way of estimating the integral, but it's probably not the best way. We're capturing a lot of extra area here, so I'm wondering if there might be some other method that we could use to estimate the integral. Well, conveniently, I've placed another graph of the same function over here. Ah, surprise! And we're going to try another estimation method. Now that estimation method is, again, to chop the interval from 0 to 5 into subintervals. I'm going to use the same number of subintervals, 5 of them. But this time, for my representative value of f over each subinterval, I'm going to use the right endpoint. So I'm going to use f of 1, f of 2, f of 3, f of 4, and f of 5. And again, I'm going to add up the sum from I equals 1 to 5. There we go, I equals 1 to 5 of f of something times delta x. That delta x, of course, still 1. What is it I'm adding up f of this time? Well, when I is 1, I'm adding up f of 1, or I'm using f of 1. When I is 2, I'm using f of 2. When I is 3, I'm using f of 3. So I think this is just I this time. So the sum I'm taking is the sum from 1 to 5. Make that a little bit nicer there. 1 to 5 of f of I times 1. And then visually I can represent that as the sum of a bunch of areas of boxes. It'll look like this. And then that sum, that's going to be my right-hand sum for this function in this interval with 5 subintervals. I'm going to call that right of 5. And I could actually add up what all those areas are going to be. I'm not doing the calculations here. I want to focus on just how we think about each estimation method. Now again, you might want to think for a moment about whether this estimate is going to be higher or lower than the actual value of the integral from 0 to 5 of f of x dx. And as you may have guessed, this estimate is going to be lower than the actual integral because this captures some of the area onto the curve. This estimate captures some of the area under this curve, but not nearly all of it. There's a whole lot of extra that we haven't accounted for. So this estimate is too low, where the other one was too high. The other one was too high. So this is turning into that Goldilocks story where, okay, this one is too hard, this one's too soft, this one's too hot, this one's too cold. And the question then becomes, let's see, this one was too high. The question then becomes, can we find an estimate that's just right? Well, if we could, we probably wouldn't need to do quite as much with analytic integration. If we could find an estimate which is exactly the right answer, we'd really be in business. We wouldn't be estimating anymore. And for this function, we're not going to be able to find the exact numerical value of the integral. But there are some estimates we can use that will get us closer to just right. So for that purpose, I have put in another copy of the graph of the function, which is right. I don't know why that one is lower resolution than the other ones. Sorry about that. Must be the way I'm using the Explain Everything app here. But anyway, for this estimate, what I'm going to do, I'm going to, again, chop the interval from 0 to 5 into 5 subintervals, same as before. But this time, instead of taking just one representative value of f, I'm going to take 2, both the left and right endpoints. And instead of drawing a rectangle, I'm going to draw a trapezoid. And then same for this subinterval, trapezoid. Make that a little bit nicer there. That's better. And then from 2 to 3 a trapezoid. And then from 3 to 4 a trapezoid. And then from 4 to 5 a trapezoid. Well, trying to get this really accurate because we're going to do some math with this in just a minute here. There we go. That's not bad. So now I have 5 trapezoids, and I'm going to find the areas of those and add those up. So I get something like this. Yeah, by the way, if I wanted to write this as a summation, I think the summation would be the sum from I equals 1 to 5. I'm still adding up 5 things. But this time, well, gee, what's the area of a trapezoid? It's the average of the lengths of the bases. So in this case, that's f of I minus 1 plus f of I over 2 times delta x. And I'm not going to mess with it beyond that. And by the way, I want to make sure and mention, this formula only works in this very specific example. It's not usually f of I minus 1 plus f of I. It just happens to be that because I'm using an interval from 0 to 5 and using 5 subintervals. So this is like the nicest possible case for formula writing. But anyway, this estimate here, this is called trap. Why trap? Because I'm estimating using trapezoids, trap of 5. And you might wonder, is this too high or too low? Well, given that the fact that the graph here, the graph of f, is concave up, we notice that the trapezoids are going to slightly overestimate the value of the integral. Each trapezoid is a little bit bigger, although only a little bit, just a little bit bigger than the actual area under the curve. And that's true on each subinterval, but as you could probably tell earlier, I was having a very hard time drawing this one so that was clear, because this subinterval here, the shape that we get by looking at the graph, it's very nearly a trapezoid already. It's very close. But this estimate is a bit too high. So I'm going to record that. It's a bit too high. But only by a little bit this time. It is actually quite a bit closer than left of 5 or right of 5. All right, now there's one more estimate that I could come up with, and that is I take the interval from 0 to 5, divide into subintervals, and then I do use one representative value of f on each subinterval, but the value I use is the value at the midpoint of the subinterval. So I use the values at 0.5, 1.5, 2.5, 3.5, and 4.5. And then I can draw the rectangles. So I get 5 rectangles. And then add up all of those areas. Now you might wonder, well, first of all, this one I call the midpoint sum, mid of 5. And I can write a formula for it. That formula would be I, sum from I equals 1 to 5, of f of, I think it's going to be the average of I minus 1 and I, so that's going to be I minus 0.5 times delta x, where delta x is again 1. And again, that formula is very specialized. This happens to work here only because I'm dealing with an interval from 0 to 5 and chopping it up into 5 subintervals of length 1. Otherwise, this would be a bit harder to come up with. But anyway, that's the midpoint sum. And you might wonder again, is this too high or too low, or just right? And in this case, honestly, it's kind of hard to tell. I drew the picture so that the rectangles are sometimes below the curve, sometimes above the curve. And you might be able to figure out from looking at this whether the parts above the curve outdo the parts below the curve or vice versa. But I think, now this is really cool. I want to show you a way that we can actually tell for sure whether this estimate is too high or too low. But it's going to require us to redraw these rectangles as something else. So I'm going to get rid of this for now. I'm going to get rid of these. See if I can erase this graphic here. Okay, yeah, I'm going to erase all of this red now, including the mid-5 and including the formula, because explain everything doesn't let me chop the red up into smaller bits. So I'm going to get rid of this. Okay, and start over. Now what I'm about to draw is the same estimate, just drawn differently. So again, I'm taking same subdivision of the interval, same representative values. I take the value at each midpoint, but this time, I'm going to draw a trapezoid that is tangent to the graph, that has a side tangent to the graph on each subinterval. That was a mess. Let's try that again. There we go. Same here. I think it helps if I start at the midpoint and then try to draw a tangent rather than trying to go through it on one go. Now if I draw the trapezoids that way, rather than rectangles, I'm actually going to get the same area, and I want to show why that's the case, because it's not at all obvious. Earlier, I was drawing this rectangle here. There we go. That was what I was looking at earlier. Now look at the relationship between this rectangle here versus this trapezoid. The difference between them is the trapezoid has an extra triangle worth of area here, but it also loses a triangle of area compared to the rectangle. But those triangles are actually the same size. You could prove that using geometry. So both the rectangle and the trapezoid have the same area, which is the whole point. I want this to be the same estimate. So this is still mid of 5, and now I'll bet you could tell whether this is higher than or lower than the integral. It is actually lower than the integral because each trapezoid is completely encompassed by the area under the curve. So this is a bit too low. And by the way, the fact that this is a bit too low, this one in particular, and the trapezoid sum was a bit too high, get those both in the same frame here. And for that matter, the fact that the left-hand sum was too high and the right-hand sum was too low, all of these things had to do with the unique shape of this graph. Sometimes the graph has a more complicated shape, and you're not going to be able to tell immediately whether the left-hand sum, for example, is too high or too low. All of this happened because of specific features of these graphs. So I want to make very clear that if I give you a graph and I ask you whether trap of 5 is too high or too low, that is higher or lower than the actual integral, you're going to have to work out, based on the shape of the graph I give you, which one of those is the case. But anyway, the purpose of this video was to introduce these 4 methods of estimation, and now I've done that. So with that, I will see you in class. Thank you for watching these videos.